Welcome back. In the last video we have covered solenoid and we found out the magnetic field generated inside the solenoid, and that magnetic field can be calculated using formula B is equal to mu naught Ni, where N is the number of turns per unit length, I is the current carrying by the coil, current carrying in the coil, right? This is a simple formula for calculating the magnetic field inside the solenoid. Now today we are going, in this video we are going to take example of toroid. What is this? Toroid is kind of cylinder. If you like, you bend the cylinder and make a circular, some circular kind of stuff like this, right? It means you have like a donut kind of structure, and you have wounded a coil around it. Then this will become a solenoid, this will become a toroid. In the toroid we'll find out what would be the magnetic field, okay, inside this toroid. Okay, similar to what we did before, is like here we are taking a one contour, and we will see how much current is there inside this contour, right? So this is what we have taken a contour over here, right? This circle is a contour, and we are going to find out how much current is going inside or coming inside, right? So if you see here, everywhere means here current is going inside, current is going inside. Everywhere is like a cross, everywhere it is like a cross, okay? And this one is dot, this one is dot, and here is cross, means current is going inside, right? Okay, now if you see here how many current, means how much current is going inside, we need to find out how much current going to, and we can find out the integration contour close integration of B around this contour, right? And the radius of this contour is nothing but a circle of radius r. It means B into dl would be mu naught total current, right? Total current. So we need to find out this integration and total current. What about this integration? This integration is nothing but you take this here, from here B, this take this here r d theta, okay? This is the r, then this length will be r d theta, then you have a magnetic field B over there, and r d theta full integration is equal to mu naught I, and then B r d theta, r is a constant, then d theta would be full 2 pi. It means you will get 2 pi r B is equal to mu naught total I. Now we'll find out total I. How much I is there? This is a toroid, okay? The current crossing the area bounded by the circle would be N into I. N is the number of turn. If we have a total number of turn N, capital N, and the current is I, then total I would be N into I, where N is the total number of turn. Okay, then what you will get, 2 pi r beta would be equal to mu naught capital N. Capital is total number of turn, it's not like total number of turn per unit length, it's capital N to I, okay? Then what you will get ultimately you will get B is equal to mu naught by 2 pi Ni by R. This is the final equation of magnetic field inside the toroid. Okay, we still have some time. We'll talk about BiotSavartLaw. This is a very, very important law. Okay, let's talk about this. BiotSavartLaw. BiotSavart. What it says? It says like, if you have a current carrying wire, long current carrying wire, okay, and if you have some point over here P, what would be the magnetic field here? This is what it says. And as I have discussed about this formula in the very first video of magnetism, dB, because of the current carrying wire, would be mu naught by 4 pi ideal cross R divided by R cube, right? This is what we have learned. And direction of magnetic field will be given by simple right hand rule. This is first vector, this one is second vector, and this one is third vector. Okay, then here magnetic field direction here, what would be, just put your finger over here, okay, your finger over here and your palm in this direction. Okay, then if you put palm in this direction, palm, then what you will get your thumb inside. You can see, you can do and see this one, your palm in this direction, finger in this direction, then your thumb will come inside this. Okay, it means magnetic field at this point P would be inside this. It's kind of penetrating directly to your screen. Okay, then what will be the value of magnetic field? This is the dB, right? Because of some fraction of current element. Then if we need to find out the magnetic field due to the current element of length L, right? Current element of length L, what we will do? This is the current element of length L. Okay, up to length L, and the distance from here to here, means from the current carrying wire to the point, is D, right? In that case our convention is something like, we take this one up to L, this is angle theta, right? This is the angle theta, this vector would be R. Okay, if you take this one into account, what you will get, L will be equal to minus D cot theta, correct? L will be equal to minus D cot theta. Then what about DL? DL will be minus cot theta D cot theta. D is a distance here, D is a distance, this distance, then D into what? D distance into cot theta by dl. This is minus D cot theta by dl. Okay, then we will get minus, that will be plus, then D into cosec square theta into dl or d theta. Okay, means dl will be D into cosec square theta d theta, right? And R will be equal to, what will be the value of R? R would be equal to this, the R will be equal to D cosec theta. This is the very important formula. If we will put this one over here, what we will get? IDL R means ideal sine theta, right? IDL sine theta. Okay, and we know the value of those things, and just put it, you will get it. Then dB will be equal to what? Mu naught by 4 pi mu naught by 4 pi. Here ideal I, your dl is d cosec square theta, d cosec square theta okay, d cosec square theta, and then your r will be d cosec theta, right? R will be d cosec theta, r will be d cosec theta divided by, and into one more thing, sine theta, because ideal cross r IDL r sine theta. Sine theta is this one, okay, ideal sine theta, and here you will get r cosec, sorry, it's a d cosec square cube theta. Okay, then what will happen? This cosec will get cancelled, one d will get cancelled, d will get cancelled, right, and this d will get cancelled. You will end up with db is equal to mu naught by 4 pi into IDL sine theta by r square or whatever, IDL sine theta, and r we have already put, and d got cancelled. Then we end up with mu naught I sine theta divided by capital D, means d, right, and d theta. So this is very important formula. Let's make it very clear. dB will be equal to mu naught by 4 pi, this is constant, keep this one here, I is the current, total current, and sine theta d theta divided by d. Okay, this you got to remember. Now you see, for this case your theta is varying, right? From where to where theta is varying? You have a wire here, right, and you need to find out from d distance, means magnetic field from d distance, and this one is like r, this angle is theta, right, this angle is theta, and this is total length L. If that is the scenario, this is the scenario, then this is the formula you will be using, right? This is theta 1, and from here it is 90, so it's changing from theta 1 to 90. You integrate it, you will get the result. Okay, the very famous formula which is derived from here is like, if we have a wire, infinitesimal wire, infinite wire, and from distance d, if you want to find out the magnetic field from distance d, and if it's making angle alpha from this end and beta from this end, then magnetic field at point P will be equal to mu naught I by 4 pi d cos alpha plus cos beta, and you will get this formula using this is exercise for you. Use this formula, get this result. Okay, see you in the next video. Bye.